so based on what I saw happen in class today being Tuesday, May 19th, we are struggling a little bit with colligative properties. So what we're going to do, I'm going to do another tutorial, in which case I'm going to take what we did in the last video, the molality, total molality, and mole fraction, and we're going to apply that to our actual colligative properties. All right, so in context, first of all, what we're going to do, so we're still on Chem question number 40, the skill practice section, and we're going to focus on number 5, right, which is kind of a full problem set, in which case we have to go from start to finish to calculate whatever you might be asked to calculate on a quiz or test. All right, we're going to go through step by step and make sure, hopefully, by the end of this video that you got the resources you need to kind of understand how to tackle these particular problems. All right, so Chem Quest 40, number 5 on that back page. That page you'll be turning in if you haven't done so already. All right, so contextually speaking, we can make predictions about what happens to the boiling point of water, the freezing point of water, and the vapor pressure of water when we dissolve something into it. All right. Now we can do that because we know those properties for pure water at various temperatures, right? So, for example, pure water at 22 degrees Celsius will have a vapor pressure of 2.6 kilopascals. That's that tendency for the actual liquid water molecules to become vapor, right? There's a little bit of pressure applied, right? We know that pure water melts or freezes at 0 degrees centigrade or Celsius, and we know that pure water boils at 100 degrees Celsius. Okay. So the whole purpose of what we're doing with our molality, etc., is to try to make predictions. Okay, what happens to our boiling point and melting point, etc., when there's not pure water, we dissolve something in. All right, and that's instructive to know sometimes. So number 5, right, is what's going to happen essentially to my boiling point, freezing point, vapor pressure if we dissolve 72.8 grams of calcium chloride into 120 grams of water. All right, so what we have to understand, this is what I mentioned on the last video, is I cannot tackle these 3 problems right here, my boiling point, freezing point, vapor pressure, until I've already calculated my molality and total molality, and then my mole fraction for the vapor pressure. Right, so again, we're going to step back, we're going to solve those 3 things before even setting into 5A, B, and C. You know, if you've got space off to the side on your sheet, right, we'll just settle those off to the side here. All right, so I'm going to start with my molality, and in order to find molality, total molality, I need to also write out my dissociation reaction, right? So calcium chloride, right, this is plus 2 minus 1, so my formula of calcium chloride before it's dissolved is just CaCl2, right? So 2 chlorines and 1 calcium make calcium chloride. All right. Now, when I dissolve it into water, you have to remember the dissociation of an ionic compound. We know this is ionic because calcium is a metal, right? Will produce the individual ions that we see in this formula. So I'm going to get a calcium ion, which has a 2+ charge. Don't forget your charges, by the way. And 2 chlorine ions, which have a -1 charge. Right? Now, the reason I need to write out my dissociation reaction in that way is 1 particle of calcium chloride actually produces 3 ion particles when in solution. And it's this side of the equation, the number of ion particles that actually affects my boiling point and freezing point, not the number of these particles individually. Okay, so keeping that in mind, I'm going to solve for molality first. All right, so if I have 72.8 grams of calcium chloride and 120 grams of water, I need my units to be moles over kilograms, right? And moles of solute and solvent. So moles of calcium chloride in this case over kilograms of water is what I'm solving for. Right, so and moles of calcium chloride will be solved as such, right? So I have 72.8 grams of calcium chloride, right? I'm going to divide that by the molar mass, which is 110.98 grams per mole, right? We get that from adding 2 chlorines and 1 calcium, that's the molar mass. That equals 0.6566 moles of calcium chloride. All right, so there is my number that goes here. Now I need to solve for kilograms of solvent, which is really easy. I've got 120 grams of water, and that equals 0.120 kilograms of water. All right, so now to decide for my molality, I'm just going to go 0.656 over 0.120, and my molality will come out to 5.47. All right, so the concentration of calcium chloride in solution here is 5.47 moles per kilogram of water. All right, so that is my molality, 5.47 moles. So I'm going to write this off to the side just because I'm going to refer back to this number, little m equals 5.47. That way I can erase some items here. All right, so next step, I've got molality. Now I'm going to do total molality. And this is not too difficult, right? And this is why I need to have that association reaction written so that I can refer to it. So I have 5.47 as my molality of calcium chloride as a whole, right? So I'm going to write my little 5.47 right there, right? That's the number we got from that first calculation. Now, what I have to understand is this is going to produce, okay, a larger total molality. All right, so in this case, I've got 5.47 molality of this as a whole. That's going to, so I've got one calcium here, so this is going to be a 5.47 as well. Plus, I've got 2 chlorine ions forming, right? So I'm going to take my 2 times 5.47. Right, so essentially, my total molality in this case is going to be equal to 1, 2, 3 times my original molality. NT will be 3 times 5.47. NT total molality is equal to, let's see, I've already done this calculation. 16.4. Sorry about that pause. All right, so that is my total molality. Now, this is the number, but my total molality is going to be the number that determines my new boiling point and new freezing point, because it's the individual particles in solution that determine how much our boiling point and freezing point are affected. All right, so I'm going to write my MT down here next to my little m equals 16.4. All right, so I've got that number locked in. Now, I can, at this point, go ahead and solve for my boiling point and freezing point, right? But I'm going to go ahead and find my mole fraction, since I'm going to have to do that anyways to solve for C, for my vapor pressure. All right, so again, I know my moles of my solute in this case, which is 0.656 moles. So my 72.8 grams of calcium chloride is 0.656 moles. All right. All right. So what I need to solve for now, which I haven't done yet, is my moles of water. Right. So I'm going to go moles of solvent over moles of solvent plus moles of solute. Sorry. Moles. Okay? So I'm trying to solve for my mole fraction of water in this case, right? And that's what's going to be important for solving for vapor pressure a little bit later. All right? So I know my moles of solute is 0.656. I just got to find my moles of solvent. So I've got 120 grams of water, right? And divide that by 18.02, which is my molar mass of water. And when I solve that, I get 6.67 moles of water. All right? So now I know my moles of solute, I know my moles of solvent. I can just plug those into my equation here. All right? So my 6.67 over 6.67 plus 0.656. Alright, and I should get a decimal that comes pretty close to 1 because that's a small addition there. So my mole fraction is 0.910, and mole fraction doesn't get any units, it's just a factor by which we're going to multiply. Right? So we're going to say x solvent over here is equal to 0.910. Now, I've done the legwork, dirty work needed to solve for those three things. And that's the easy part. Once I've done this work here, right, the rest is easy peasy. Alright, so I know my molality, I know my total molality, I know my x solvent. So I'm going to solve for my boiling point first, right, for letter A. So A, boiling point. So delta T BP. So change in temperature and boiling point is going to be equal to my NT times my boiling point constant, which is 0.515. Alright, so I'm going to solve for my change in boiling point. Alright, I know my boiling point constant for water, and I now know my MT because I just solved for it. It's this number right there. So my change in boiling point will be equal to 16.4 times 0.515. So my change in boiling point is equal to 8.45 degrees Celsius. Now, keep it in mind, this is my change in boiling point. The question is, what is the actual boiling point? So we have to then remember that my pure water boiling point is 100 degrees Celsius. When I add this much solute, I'm going to increase my boiling point by 8.45. So my actual answer will be 100 plus 8.45, which will give me 108.45 degrees Celsius. And that is my answer for letter A. So again, find my change in boiling point, add it to 100. Done. Okay, letter B, my new freezing point. All right, so similar equation, I just have a different constant. Letter B here, change my freezing point. So my change temperature FP will be my total molality times 1.853, right? And that 1.853 is my freezing point constant for water. All right, so I've got those two values, so delta TFP will be equal to 16.4 times 1.853, right? And that gives me 30.4 degrees Celsius. All right, which means in this case, since my normal freezing point of water is 0, I'm going to go 0 minus 30.4, which will give me a negative 30.4 degrees Celsius. Alright, so by adding that much calcium chloride, that means it's going to have to be 30 degrees colder than normal water in order to freeze. Alright, which again takes us back to why we add salt and stuff to the sidewalks and roads to melt that ice. We're not really heating the ice up, we're actually changing the freezing point of the water so it's no longer cold enough to keep that water frozen in the ice form by adding that solute. Alright, pretty simple way to melt some ice and keep the roads a little safer. Alright, now last but not least, letter C is our change in vapor pressure. Okay, and again, it's a fairly simple process. We're just taking our mole fraction and multiplying by the vapor pressure of normal water. Alright, so my P solution, so that's my mixture, is going to be equal to my mole fraction times P solvent, which is the normal vapor pressure at that temperature. Alright, so my X solvent has a factor of 0.910, it's going to be 0.910. Right, the vapor pressure of water at 22 degrees Celsius is 2.6 kPa. So my new vapor pressure should come out to 2.37 kPa. And that's it. Alright? So, if you guys just spend some time as you tackle these problems, get good at molality and total molality and mole fraction. That's the the legwork. Then you just plug those numbers in, and you can make that prediction. And there we go. All right. Best of luck to you. Hopefully we got this figured out soon.